go ahead and get done as quick as possible tonight and get out of here and start enjoying your fall break, I suppose. So let me get connected here. Okay. All right, so we're getting into Halloween season, so I thought the most scary thing that I could get for you in math would be fractions. So that's what we're doing tonight, is fractions, the scariest thing in math. All right, so we're going to talk about rational functions tonight. Both sections together talk about rational functions. The first section is a lot of information, but when we get to the second section, it's the same stuff again. Just they add one or two things to it. So we can get a lot of information here in the first section. The second section is just kind of repeating a lot of that. So we're going to deal with rational functions. What that means is we're dealing with a polynomial in the numerator and a polynomial in the denominator. That's a rational function. With the domain of a rational function, since we're dealing with a fraction, it's a polynomial in the denominator, so that means it has a variable. And that's one of our red flag things for finding a domain that we talked about earlier in the course. So the domain, to find that, you set the denominator equal to 0. Really, really simple idea. The same way we did back in chapter 3. And then solve, obviously. And that gets you the things that x cannot be out of that. The next thing that you want to do after you find the domain would be simplify. The fraction. And what I mean there is you're going to take the factored form of both the numerator and the denominator and try to cancel a factor out if possible. So that's going to involve factoring. We'll look at that some as we go through there. If something does cancel out, what that creates are holes in the graph. It's created at the x values that were canceled. Through simplifying. That won't happen every time. In fact, it's a rarity that it even does happen, but you do have to look for those things. So domain, then you're going to try to simplify by factoring numerator and denominator. Hopefully when you're finding the domain, you're using factoring anyway, so it kind of speeds you up a little bit. And then once you've got the factoring done, any factor that cancels is going to cause a hole to exist in the graph. And it's not going to be, like an asymptote or something. We'll get to that in a second. It's going to be like an empty spot that's just an empty circle in the graph. Like the line will be going to it. There'll be an empty circle, and then we'll keep going. That idea, that happens with these particular types of things. And then you'll have your asymptotes. And there's 3 different kinds of asymptotes. There are vertical asymptotes. Those come through the denominator. Your vertical asymptotes can occur on any rational function through the factors of the denominator, causing vertical asymptotes to exist. You want to look at those factors of that. So like if you had x plus 4 as a factor in the denominator, that means x equals -4 is a vertical asymptote. It makes a vertical line out of that. We'll see that when we get some examples of it. But vertical asymptotes can exist on any rational function. Horizontal asymptotes they don't exist all the time. They exist if the degree, what's the degree of a polynomial? Highest exponent. So if the degree of the numerator is less than the degree of the denominator, if that's what's happening, if you've got a degree of the numerator, for example, f of x is x squared plus 9x minus 3. That's our numerator. Our denominator just needs to be bigger than that, x cubed plus 1, something like that. That's an example of a rational function that fits having a horizontal asymptote. It has a horizontal asymptote at y equals 0 in the horizontal asymptote. Okay. Degree of the top smaller than degree of the bottom. Doesn't have to just be one smaller. If you had x over x to the fifth, that's still got y equals 0 as a horizontal asymptote. Just as long as the top has a smaller degree than the bottom, it's y equals 0. That's always going to be the case with horizontal asymptote, with that horizontal asymptote. So another case for a horizontal asymptote is if the degrees are equal. The degrees of the numerator and denominator are equal. Then the horizontal asymptote is at y equals, we'll call it a over b, and that's just shorthand for coefficients of the degree or the leading term. Example of that would be something like, you got f of x is equal to 3x squared plus 5x minus 7 over 4x squared minus 2x plus 13. Something like that. Your degrees are exactly the same on top and bottom. Again, we're looking at the simplified rational function. Not, it should work also on the original, but you want to look at the simplified. Leading coefficients are 3 and 4, so the horizontal asymptote would be at 3/4. So two cases where you could have a horizontal asymptote. One of them is where the top has a degree smaller than the degree of the bottom. Then it's y equals 0. If the degrees are exactly the same, then it's the ratio of the leading coefficients. That's the way you would think about that, okay? This one is y equals 0. That one is the ratio of the leading coefficients. Those are the two cases for horizontal asymptotes. One other type of asymptote is called an oblique asymptote. You may have heard them called slant asymptotes. You may hear me call them slant asymptotes. We called them slant asymptotes back in the day. They can use the word oblique now. Slant seems to describe them better to me than oblique does. Slant asymptotes are linear pieces. There's only one case where that happens, and that's if the degree of the numerator is one more than the degree of the denominator. in long division, we'll do some of that. We'll find the oblique asymptote. It'll be in the form y equals mx plus b. It'll be a line in slope-intercept form is what it'll look like. Example of a polynomial or rational polynomial function, f of x cubed plus 27 over x squared plus 9. That is an example of a rational function that would have an oblique asymptote. Okay, we'll find that one on that one. But one key thing to remember is that horizontal and oblique asymptotes never occur together. There's no way that you would have an oblique asymptote and a horizontal asymptote. Vertical asymptotes can occur with either of these, but horizontals and obliques will not ever occur together. All right? And the cases for them make sense why they would never occur together, because if the degrees are the same, then it has to be a horizontal. If the degree of the top is smaller than the bottom, it has to be a horizontal. The only time an oblique occurs is if the degree of the top is one more than the degree of the bottom. Yes, sir. So it's always one or the other? It won't always be one or the other. It could be neither of those. There are times where you don't have a horizontal or an oblique. An example of one where you would have neither would be something where you have like an x to the fourth in the numerator and x squared in the denominator. It's more than one above it. It doesn't fit either of the cases for horizontal. So you don't have to have a horizontal and you don't have to have an oblique. If you have one of them, you will not have the other. So that's a really good question, because that does happen. Verticals usually are there. There's usually vertical asymptotes. Not to say that there aren't times that vertical asymptotes don't exist, but in our course, they tend to put them in there. All right, so let's look at some problems and let's do those things. So all of these things that we wrote down here, we're going to find the domain. We're going to simplify the expression. We're going to see if there are any holes in that expression. Then we're going to look for those asymptotes, the verticals, the horizontals, or the obliques. Or if they don't exist, none of those. Okay, so we're going to do all of those things for a few examples here and try to get some practice at that. And I think once you see it, you're like, oh, it's not that bad. It's a lot of stuff, but it's not just incredibly difficult. So let's start with this one. F of x squared plus 7x plus 12 over 4x squared minus 1. My twos are not looking right tonight. All right. So the first thing that I would do, and this is just me trying to teach you a process to go about solving these and working that, is I'm going to try to find the domain. And to find the domain, I'm going to try to use factoring if at all possible. Not that factoring is the only way to solve 4x squared minus 1 equal to 0, but I'm going to try to use factoring because I know I want to try to simplify the rational function, and factoring is the way to do that. So try to factor at all costs here, just to save yourself a little work at every step, because it is a lot of work to do one of these. So if I factored that, that's a difference of squares. 4 is 2 squared, 1 is 1 squared. So that's actually 2x plus 1 and 2x minus 1. So over here, I'm just going to rewrite the function with 2x plus 1 and 2x minus 1 in the denominator. I'm going to go ahead and solve these. 2x plus 1 equals 0. 2x minus 1 equals 0. I know that x is going to equal negative 1/2 and x is going to equal positive 1/2. Those are the x values that are eliminated in the domain. So if I'm going to write the domain over here. That's part of my job, is finding the domain. The domain are all x's as long as x does not equal plus or minus 1/2. That'd be a shorthand way of writing that. What would that be in interval notation? We need to be able to do all of the notations here for that. Even though set's a lot easier, but interval notations. Is negative 1/2 included?
Yes.
It is? No, x can't be negative 1/2. So we have to have a parenthesis there. U. Pick back up at the negative 1/2 and then go to the positive 1/2. Union, and then start again right after 1/2 up to positive infinity. So there would be the interval notation for that. Be able to bounce back and forth between those two to find that domain. Okay. Now, after you find the domain, the next step before you do your vertical asymptotes is to try to simplify. So we need to try to factor the numerator if we can. Not saying that we always will be able to, but it is nice if it does. It helps us to find those asymptotes. So x squared plus 7x plus 12, things that multiply to be 12 and add to be 7. 3 and 4. So x plus 3, x plus 4. Now, do any of those factors cancel out? No. Didn't help us that time, but that's just one of the things you've got to try to do is try to simplify it. So factoring is the way to do that. Now, because it didn't simplify, that means that we don't have any holes. So we just say none there. Just shows that you've looked for them. Okay. If one of the factors had canceled out, the hole would be at that value, that x value, like if x plus 3 had canceled out, it'd be a hole at x equals negative 3. That's where the holes exist. And we'll get to one that maybe has one in just a little while. All right, so there's that. The next thing would be vertical asymptotes. And we'll start abbreviating this after this example. Vertical asymptotes. Vertical asymptotes are going to match your domain if nothing canceled out. Okay, so what were the x values that we got, or the equations we got for those for our domain? If nothing cancels out, your vertical asymptotes are those. So there's vertical asymptotes at x equals positive 1/2 and x equals negative 1/2. If one of those factors cancels out, then it can't be a vertical asymptote. Does that make sense? That if it canceled, it can't be a vertical asymptote. If you get kicked out of the game, you can't play anymore, right? So if you get canceled out, you can't be a vertical asymptote. So that's why the simplifying has to happen before you start finding those. Okay. All right. Now, originally, what was the degree of the numerator and the denominator? 2 and 2, right? Both of them were squared. Does that mean it has a horizontal or an oblique or neither of those? Horizontal. If the degrees are the same, there's going to be a horizontal asymptote. So we're going to have horizontal asymptote. At the ratio of the leading coefficients. So if we look at the original problem, there's a 1 in front of x squared. The leading coefficients are 1 and 4. So the horizontal asymptote will be at y equals 1/4. Because we have a horizontal asymptote, what do we know about the oblique asymptotes? Can't have them. So we just say oblique asymptote. None. Can't have those. Okay. So there we have found the vertical asymptotes, the horizontal asymptote, and then we know that it doesn't have an oblique if it has a horizontal. Okay. Found the domain for that as well. Okay. Most likely on quiz or Canvas quiz and on the test, I'm not going to ask you for all of these things. I might ask you for one of those things. What's the oblique asymptote for this one? One of the answer choices might be none. So, being able to recognize that. But it does take going through this process to get there. Let's do another problem. I got that from the leading coefficients of because the degrees were the same, both of them were squared, you're going to take those two numbers in the front. And the ratio of those, that's going to be the horizontal asymptote. All right. Example B. Let's take another function. Let's do x squared plus 7x plus 10 over x cubed minus 25x. That's the denominator. And we're going to find those same things. We're going to find the domain. We're going to find the holes if they exist, the vertical asymptotes, the horizontal asymptotes, and the oblique asymptotes. Just abbreviate those there. Save us a little work. All right, so back to the original. We're going to find the domain of that. That's our first job. What do we need to do? How do we find the domain? Okay, how so? Factoring. Okay, so if I factor that, what's my first step in factoring x cubed minus 25x? So the first step in every factoring problem. You look for a greatest common factor, which is x. And then we'll x squared minus 25 factor. Yes, it's a difference of squares. So that the factored form of the denominator is x, x plus 5, and x minus 5. I'm just writing that right next to it because I'm going to factor the whole rational function anyway, if possible. And then I'm going to use that factored form to find the domain. So when I go to find that domain, I'm taking each factor from the denominator and doing what with it? Setting it equal to 0. Absolutely. So x equals 0, x plus 5 equals 0, x minus 5 equals 0. That gets me 3 values that x cannot be for my domain. X can't be negative 5, x can't be positive 5, and x can't be 0. X can't be 0. So set notation, that's pretty easy. X does not equal 0 or plus or minus 5. If I went to interval notation, negative infinity up to negative 5. This one's actually really long. Negative 5 to 0, 0 to 5, 5 to infinity. That's a lot of stuff for interval notation, but recognizing both. All right, let's factor the numerator if possible. So it's a trinomial. I'm thinking what multiplies to be 10 and adds to be 7. Yeah, x plus 2 and x plus 5. All right. And now, what cancels? An x plus 5 cancels an x plus 5. Okay. So that creates a hole. So there's a hole here at x equals negative 5, right? Now, vertical asymptotes. Because the x plus 5 canceled out, it can't be a vertical asymptote. It became a hole. So the vertical asymptotes are where? X and then x minus 5 make vertical asymptotes. Their vertical asymptote is what they would equal if you solve them, if you set them equal to 0. X equals 0 is a vertical asymptote, and x equals, we had the minus 5 left, so it's x equals positive 5. Those two equations make your vertical asymptotes for this problem. So one of them is right on top of the y-axis. The other one is over at 5 on the x-axis. There's a vertical line there. We canceled out the x plus 5, right? So if you set x plus 5 equal to 0, you get x equals negative 5. If you set x minus 5 equal to 0, that's where we get x equals positive 5. That's these are your possible vertical asymptotes, are those equations where x is by itself. All right, would this have a horizontal asymptote or an oblique? Or neither. Could be neither. Horizontal at, what's the degree of the top? Originally, it's 2 and 3 on the bottom. At the simplified step, we've got x up here and then x times x down here. So it's 1 and 2 if we look at the simplified version. So it still follows the same rule, that the top is smaller than the bottom. If the top is smaller than the bottom, the horizontal asymptote is always at what? Y equals 0. That's coming from right there, that line there. If the degree of the numerator is less than the degree of the denominator, then the horizontal asymptote will always be y equals 0. Always. Doesn't matter how much smaller. One of them is degree of 3 and the other one's degree of 17. If the top is 3 and the bottom is 17, it's still y equals 0 for the horizontal asymptote. And because it has a horizontal asymptote, we know that it can't have an oblique asymptote. All right. Horizontals do not occur with obliques. Okay. Any questions about those? Let's look at the graph of that. If you graphed the original problem on the graphing calculator, just to show you kind of how some of this shows up. Being careful on your typing that into the calculator, you need to put parentheses around the numerator. So our numerator was x squared plus 7x plus 10. And I put parentheses around all of that and then do division and then put x cubed and minus 25x in parentheses as well. If you forget the parentheses, things are not going to work as you intended. Weird looking graph, but here's what we can see. Right here, you can see the graph turning and going up. If you zoomed in, you're going to see this line continuing, but getting closer and closer to that vertical asymptote at x equals 0. Right here, you see the graph kind of, it gets to, right on that line, but it never really crosses it. That's our horizontal asymptote at y equals 0. Right here, this line right here, what's that point right there? That's 5. That's the x equals 5. That's that other vertical asymptote. We can see those showing up in our graph. Your graphing calculator won't draw them when you just graph that original rational function, but you can see where they exist. You can see that happening because the graphs are going to show you kind of these curves happening and a space between them. That's what the graph's going to look like. Okay. All right. Let's do another. Another problem means another page, right? They take up a lot of room. So let's do one. 8x squared plus 26x minus 7 over 4x minus 1. This is kind of an interesting one. Again, we're going to find domain, holes, vertical asymptotes, horizontal asymptotes, or oblique asymptotes. This is a little different. All right. What's the first thing we should do? Set the denominator equal to 0, solve it. That's finding the domain. That's the first thing we're going to do. So if I set 4x minus 1 equal to 0, I don't have to factor it because it's just a plain 4x minus 1. Just solve it. So that's going to be x equals a fourth. So our domain is x cannot be a fourth. Negative infinity up to a fourth. Fourth. A fourth. Up to infinity. That was a little better on the interval notation. Not too bad. The next thing we do, simplify. So we got 4x minus 1 on the bottom. That won't factor any further, but the numerator possibly would. It's a quadratic, so I'm thinking maybe it will. If I do my x thing, negative 56, and add to be 26. Multiplies to be negative 56 and adds to be 26. There are two numbers that are pretty good ways apart. I know 56 is even, so I'm guessing 2. And 2 times what is 56? 28, right? So if I wanted to add to be positive 26 and multiply to be negative, I need one of those to be negative, and I want the 2 to be negative. So those two numbers work, but I got to do some grouping first. So that's why I left all the space here, because I knew I was going to have to do that. So plus 28x minus 2x minus 7. And then group that. Those 8 and 28 have 4 in common and an x. So that's going to leave 2x plus 7. Those two, only thing they have in common is a minus sign. So I'm going to pull out a negative 1. And that leaves me the right thing in parentheses. And there's 4x minus 1, 2x plus 7. That's the factored form. So 4x minus 1, 2x plus 7. All right. What happens here? Okay, so that creates a hole at x equals 1/4. That's coming from setting the factor that canceled out equal to 0. We had already done that with the domain, just happened to be the same one. So there's a hole at x equals 1/4. Because that denominator canceled out, are there any vertical asymptotes? There's nothing left in the denominator. No, there can't be any vertical asymptotes. And we're looking at the simplified version here. So the degree of the numerator is 1, and the degree of the denominator is 0. There's not anything in the denominator. So will we have a horizontal asymptote if there's nothing to compare to? No, can't be a horizontal asymptote. And technically, there's not an oblique asymptote either, because there's not a denominator left. Everything canceled out. Had there been a denominator left, we would have needed to do some long division, which we'll do. The next section we'll do. Problem where we got to do that. Okay. All right. Okay. So section 5.4 is about the domain, the asymptotes, all of that. Though that's its focus. And now section 5, we're going to add a little bit to that. Okay. So section 5.5 is just titled More Rational Functions. So we're just going to add some stuff to that. We're going to do all of the same stuff. We're going to find the domain. We're going to simplify. You know, inside of that, we'll find the holes that exist. We're going to find the asymptotes. And then we're also going to find the intercepts. And then we're also going to find if the graph crosses the asymptote. Okay. Put that in parentheses. Not always more than one. Okay. So all of these things we've done before. We're adding intercepts and we're adding if the graph crosses that asymptote, and we'll see how that goes. Okay, so we're going to get some more practice doing what we were doing, and then build up to more difficult problem. All right. So let's just get into an example. Try to get you out of here a little early today, I think. X squared minus 4 over x squared plus 5x minus 14. Little fun problem. Okay. So we're going to do all of those things. Again, domain, holes, to vertical asymptotes, horizontal asymptotes, bless you, and oblique asymptotes. And then we'll answer the question, does it cross? Okay? So first things we do, what? Yeah, break down the denominator by factoring if possible. What if it won't factor? How do we still get the domain? This one will factor, but what if it won't? And it's quadratic. What can you do? Quadratic formula works great. If it's cubic and it won't factor, work it like a polynomial, like we did last week. Sections 5, 1, 2, and 3. Work it like a polynomial. So if it won't factor, there's still some things you can do. You're not stuck. You still have a particular set of skills to break that polynomial down, whatever you need to do. This one will factor. It factors nicely as negative 14. Add to be 5. That'd be x minus 2 and x plus 7. Is that right? 7 times negative 2 is 4, negative 14. 7 minus 2 is 5. Yeah, that's the right 2. Does the numerator factor? We'll go ahead and do that. X squared minus 4. It'd be, yeah, x plus 2 and x minus 2. Doesn't matter what order you put that in. Okay. Before we simplify, we're going to find the domain. Don't simplify until after you've found the domain, even though you know something's going to cancel here. Domain has to happen first. Okay. X cannot be 2 or negative 7, and my brain won't let me do it that way. I got to put negative 7 first. And we'll just stop. We won't put that in interval notation just to save us time, because I think you can do that. It's just
plus or minus 2?
No. Would only be positive 2 because we only have x plus x minus 2 as a factor. So when you set that domain is coming from setting x plus or x minus 2 equals 0 and x plus 7 equal to 0. So that's x, this is where the x equals 2 and this is where the x equals negative 7. That's where those are coming from. Now the numerator, there may be some plus and minus that comes involved there, but the denominator is the only place we're getting the domain from. Okay. All right. And then we simplify. What part simplifies? X minus 2. So what x value is the whole exists in that? At 2. Now, one of the extra steps that we add in section 5 is that they want to know the actual ordered pair of that. They don't want to just know that there's a whole when x is equal to 2. They want to know what point is that? What's the y value that goes with that? So how do we find a y value for x equaling 2? Plug it back in. Where are we plugging it back into? Are we working with the original anymore? The simplified. So you could plug it back into the original. You'll get the exact same answer. We can't. Well, you won't get the exact same answer. Because if you plug it back into the original, you're going to get 0 on top and bottom. Because what happens when you plug a 2 into x minus 2? 2 minus 2 is 0. And it cancels out. So you have to go to that simplified version to get the y value. So we're going to plug that in to the function f of 2 equals 2 plus 2 over 2 plus 7. 4/9, yeah. So that's the y value for the ordered pair for that hole. So you actually know where on the coordinate plane that empty circle exists. That's what the hole means. Is an empty circle in the graph at 2 4/9. Okay. And I'll show you on the graph on the calculator in a minute what that actually does if you trace that point. Okay. All right. From there, the simplified version, x plus 2, and it might help you to just be less confused if you go ahead and write it like that. X plus 2 over x plus 7. Would this have a horizontal or oblique asymptote? They're the same degree, so it's going to have a horizontal at, this should be a hint, at 1 over 1, the ratio of those leading coefficients. The degrees are the same, so that tells me it's horizontal at y equals 1. I skipped vertical. What's vertical? What's the vertical asymptote from the simplified version? X equals -7, yeah. Notice your vertical asymptote. Every time we've done, this is the fourth problem. Every time the vertical asymptote is one of the numbers from your domain. It may be all of the numbers from your domain. Yes, ma'am.
So like if there's more than one still left in there, it's both.
Yes, absolutely. If anything that's not canceled out in the simplifying step that's left in the denominator will be a vertical asymptote. That is absolutely correct. So since we had a horizontal asymptote at y equals 1, what do we know about oblique asymptote? There's not one. Okay. So the last thing we want to answer here for section 5 is they ask, does the graph cross the horizontal asymptote? So I'm going to ask that question. Does f of x cross the horizontal asymptote? That's that additional question from section 5. Now, if we look at the graph of the original function, I'm just going to graph the original, parentheses x squared minus 4 minus 4 divided by x squared plus 5x minus 14. Where's our horizontal asymptote at? Y equals 1. So it would be this line right here. Can we tell if that's going to cross it or not? If we zoomed out indefinitely, we would maybe be able to tell. But can we ever get to infinity? No. So really, by looking at the graph, there's not a way to tell if it's ever going to cross it. But algebraically, there is. With the actual math that's happening, there is. So what you would want to do in order to determine the answer to this question is you take the simplified version, x plus 2 over x plus 7, and set it equal to that horizontal asymptote, y equals 1. I'm setting it equal to 1. And I'm going, if I can find an x value that gives me an answer, then it crosses it. And that would tell me the x value where it crosses it. But if it doesn't have an answer, then it doesn't cross it. So if I'm going to solve this, I would multiply by x plus 7. That cancels out. That's x plus 2 equals x plus 7. If I do distributive property with the 1, And then if I go to solve that, my instinct is to move x, right? And then the x's cancel on both sides. Does 2 equal 7? No, that's no solution. So the answer to this, does it cross the horizontal asymptote? No, it does not. If we got it, go ahead.
What about intercepts?
We're going to get those in just a second. Okay. Crossing the asymptote, you set it equal to it. If we had an oblique asymptote, we would set the simplified version equal to the oblique asymptote and solve it the same way. Okay. We can determine if it crosses it algebraically. Graphically, yeah, sometimes you can, depending on where it's at. But like this graph, it's just barely creeping up toward 1 indefinitely. It looks like it might cross it, but we've come to find out, mathematically it does not cross it. So you've got to do that math to get it there. Okay, so determining if it will cross it. Rational functions can cross horizontal or obliques. They don't cross verticals. Okay, so we're never going to answer that question, does it cross the vertical asymptote? It only crosses horizontals or obliques. And it doesn't often cross those, but we've got to check it because sometimes it does. Okay. All right, so let's finish off the problem by finding the intercepts for that. And that's, in most ways, the easiest part. What kind of intercepts are we looking for? What kind of intercepts are important in functions? X and Y intercepts. So we're going to find both of those. So let's find the X intercepts. How do you find X intercepts? When Y equals 0. So you set the simplified function equal to 0. What ends up happening here? When you multiply by x plus 7, you really only set what part equal to 0? X plus 2, which is the numerator of the rational function. That's going to happen every time. When you go to find the x-intercepts, technically this is what's happening. You're setting the entire problem equal to 0, but every time the denominator goes away and you just set the numerator equal to 0. That's what practically you're doing. So x plus 2 equals 0, and that would be x equals -2. So the x-intercept is at -2, 0. Or an x-intercept. Doesn't necessarily mean you'll only have one. Sometimes you'll have more. And then the y-intercept, how do you find y-intercepts? Plug what in for x? Nope. Find a y-intercept, you plug a 0 in for x. So instead of x, you put a 0. 2/7, right? So it'd be at 0, 2/7. Those things can be verified on the graph. If I hit trace and type a 0 in for x, 2/7 is that's the decimal for 2/7. It's 0.2857. -2, I trace that. There it is. The whole we found was at what x value? What was the x value for the whole? Wrong set of notes. +2. So if I go to positive, if I trace +2, notice what it does here. It doesn't give me a y value for that. It doesn't even put the cursor there. That's a hole in the graph. That's how you can verify your hole is correct. That +2. X being +2 is right here. It should be something there. Should be 4/9, right? That looks like it's just a little bit above half, right? 4/9 is a little bit more than half. Or a little less than half, actually. Sorry. No, yeah. Less than half, sorry. It's a 1,000 a figure on the 5-year thing. So no math involved. So this is where that should be. It doesn't give you a y value for it because that's the hole in the graph. You can always verify your hole being at the right spot by tracing that x value. If you don't get a y value back, you're probably right. Not likely that you randomly come up with a number and get it there. Okay. Let's do another. Yay. So get out another piece of paper. Let's do some more work. Let's do this one. 6x squared. I'm calling this one g of x. 6x squared plus 9x over 3x minus 2. We're going to do all of those things. So let's start with the domain. No factoring involved in the denominator, so I'm just going to set 3x minus 2 equals 0. Solve it. X can't be 2/3. The denominator doesn't factor, but the numerator does. It factors the GCF of 6x squared and 9x would be 3x, but that leaves 2x plus 3. Similar to the denominator, but not the same. So what does that mean about simplifying? It can't, which means what about holes? There aren't any. Okay, so tie that stuff together there. Okay, so holes, none. Vertical asymptotes. Where's the vertical asymptote for this one? 2/3. X equals 2/3. It's exactly the same as what we got when we found the domain up there. It's exactly the same because nothing canceled out. That it matches the domain exactly. Okay. We got the vertical asymptote. What about horizontal asymptote? Does it have a horizontal asymptote? Look at our degrees. We got a squared over a first. So it's not a horizontal. Is it an oblique? Yes. Yeah, because the difference in the top is one more than the bottom. So this is where we got to do the long division. Long division with polynomials. Fun stuff. All right. Loosen up. Get ready. This is easy. So we're taking what's on the bottom and putting it on the outside. And then we do that fun long division symbol that you used to do in 3rd grade. And we put the numerator in the top. That's 6x squared plus 9x. I'm going to put a plus 0 out there. Anytime you're going to divide polynomials, you want a representative from every power, starting with the biggest one they give you. Okay. So on the outside, they gave me a plain x, so I need a plain x and then something with no x's. This one, they gave me an x squared, so I need an x squared, a plain x, and then something with no x's. So that's why I put the 0 there. Now, long division with polynomials, you look at the first term and you say 3x. What times 3x would get me 6x squared? Do I need an x squared? I already got one x, so I just need one more. So I need a 2x. I'll put that up there. Then, just like long division from 3rd grade, you multiply 2x times what you're dividing by. But you're dividing by a polynomial, so it's like distributive property. So 2x times 3x is 6x squared. 2x times -2 is -4x. And just like 3rd grade long division, you do minus. I put it in parentheses every time, so I don't forget that I'm subtracting that whole thing from the polynomial above it. Okay? And then subtract. 6x squared minus 6x squared cancels out. That should happen every single time. If it doesn't, you're not doing it right at all. Okay? And then 9x minus 4x. 13x. Then I'm going to bring it down to the next term. Technically plus 0. And then I look at the first term again. What times 3x would get me 13x? It's a little bit more difficult. But it's the same process every time. 4 times 3 gets me 12. 4 1/3 would get me 13. So I'm going to do that as an improper fraction. 4 1/3 would be 13 over 3. And if you're ever unsure, you just divide this leading coefficient by that number in front. 13 over 3. Where that's coming from. And then distribute again. 13 over 3 times 3 is 13. That's what we meant to happen. Then 13 over 3 times negative 2. That's a little more difficult. That's negative 26 over 3. Parentheses, subtract. The 13x's, yeah, they cancel out. That's what we wanted to happen. And then that's positive 26 over 3. You're done after that because you've created a slope-intercept form piece up here. And that's what you need. An oblique asymptote will always be y equals mx plus b. That's y equals mx plus b. That's our oblique asymptote up here. Y equals 2x plus 13 over 3. That's our oblique asymptote. This is the remainder when you're doing your division. Yes, sir.
So you just kind of just leave that.
Yeah, the remainder does not matter at all.
You're just trying to get them.
That's exactly what I'm after. I don't care what the remainder is. I knew it didn't go into it to begin with because nothing canceled. So the remainder is just kind of we don't care what the remainder is. We know there's some stuff left over. That's fine. We're after that y equals mx plus b for the oblique. That's all we're after there. Okay? So once we get the oblique, we can answer the question, does the graph cross the oblique? A little bit more difficult because it's an oblique and it's got an x in it, not just a number. So we're going to take the simplified function. I'm just going to go back to the multiplied out, 6x squared plus 9x over 3x minus 2, and set it equal to that oblique asymptote, 2x plus 13 over 3. Okay. Does the graph cross the OA? All right. Multiply by 3x minus 2. Now this makes it a little more difficult because you got a polynomial over there to multiply by. These cancel. There's 6x squared plus 9x. Distribute, be 6x squared minus 4x, and then plus 13x minus 26 over 3. And then to solve this polynomial equation, what do you need to do? Get it equal to 0, okay? So I'm going to go ahead and simplify first. I got 6x squared plus 9x on that side. So if I subtract 6x squared, what happens to it? Cancels on both sides. If I subtract 9x, what happens to it? Cancels on both sides. That leaves me 0 on that side. And what on the other side? Negative 26 over 3. Does 0 ever equal that? No. That means there's no solution. So the answer, does it cross it? Is no. If you had gotten x equals something, then it's yes, and you would have the x values for where it crosses. But it doesn't. Okay. Now, last thing we got to find is what? Intercepts. All right. Intercepts, not the hardest thing we do. I think that is the hardest thing we do. So x-intercepts, set the whole thing equal to 0. So I'm going to go to the factored form. 3x, 2x plus 3 over 3x minus 2 equals 0. We can take that shortcut, and we know which part of that do we just set equal to 0. The top, that part. 3x equals 0. 2x plus 3 equals 0. Looks like we're going to have two x-intercepts. One at x equals 0. One at negative 3 over 2, right? So the x-intercepts are at 0, 0, and negative 3 over 2, 0. Two places that it's crossing the x-axis. The origin and negative 3 over 2, 0. Let's find the y-intercepts, or y-intercept. I don't know how many there are. Plug in a 0 for the x. 3 times 0, 0, or 2 times 0 plus 3 over 3 times 0 minus 2. That's just going to give us 0 over negative 2, which is 0. The y-intercept is the origin as well. Makes sense that it's the x-intercept and a y-intercept. They're both, that's the only place that it can be the same point. Okay? So here we have the x-intercepts, we have the y-intercept, we have an oblique asymptote. If we look at the graph of this thing on the graphing calculator, that's what we want to do. Just so we verify some of this stuff and so that you can see it happening. Divided by 3x minus 2. Okay. All right, there's some other stuff that you can't see there. I'm gonna graph that oblique asymptote 2x plus 13 over 3. Look how that line goes up to it right there. That should be what's happening there. You should be able to see, oh, if it does that kind of thing, I know it's got an oblique asymptote. So if you look at the graph of the original before you even start, it should give you an idea of what you should be finding on the end of that. If I zoomed out, you would be able to see a little bit more. Yeah. There's another side there. The top, that's just me zooming out, just one step from the origin. You see this piece and then this piece here, they reflect there. And then if you traced our x-intercepts at 0, there's 0, 0. If we trace the x-intercept at negative 3 over 2, there's where it's crossing the x-axis there. And then our y-intercept is also at 0, 0. So we've already done that one. Let's do one more, and we'll be done for today. All right. Example C. F of x is equal to 3x squared minus 9x over x squared plus x minus 12. What do we know about this one just by glancing at the original? It's going to be a horizontal asymptote where? 3 over 1, yeah, at 3. Y equals 3. We know that from looking at the original. If everything doesn't cancel out, and obviously everything's not going to cancel out. So that's knowing that's going to happen. Let's go ahead and get there. Let's find the domain. So to find the domain, I know I'm going to factor the denominator if possible. How does that factor? X plus 4 and x minus 3. So the domain is going to be x plus 4 equals 0. That'd be x can't be negative 4. Said x minus 3 equal to 0. X can't be 3. Does the numerator factor? How? Well, x is in common between them, but what else is in common between 3 and 9? 3. So we need to pull out the 3 with that x. And that would leave x minus 3 in parentheses. So would get us some cancellation happening there. Okay, so those cancel, which creates a what? Hole at x equals 3, right? If there's a hole at x equals 3, what's the y value that goes with that? We're taking 3x over x plus 4 and plugging in a 3. 9 over 7. So holes at 3, 9/7. Vertical asymptote. I'm going to write the simplified version there. Maybe that makes it easier. What's the only thing left in the denominator? X plus 4. If I set that equal to 0, it's going to get -4. So it'd be x equals -4. That's my vertical asymptote. The x minus 3 canceled out, so x equals 3 can't be a vertical asymptote. It's gone. Y'all said it had a horizontal asymptote at y equals 3. So oblique asymptote would be none. And does it cross the horizontal asymptote? We're going to set 3x over x plus 4 equal to 3. Now, why did I put 3x plus 4? It's just x plus 4. So that's going to be 3x equals 3x plus 12. If I try to solve that, it's going to be 0 equals 12, which is no solution. So does not cross. The horizontal asymptote. My handwriting is getting worse. It goes on here. Does not cross the horizontal asymptote. If we get a number that says x equals, then that's a yes, it does cross the horizontal asymptote. And that at that x value. Okay. Last thing we're going to find is intercepts. So how do we find the x-intercepts? Set the what equal to 0? Numerator. That's easy enough. X equals 0. So our intercept is at 0, 0. For the y-intercepts, we plug in a 0. 3 times 0 over 0 plus 4. That'd be 0 over 4, which is 0. So the 0, 0 is a x-intercept and it's the y-intercept. So it's the only intercept we have is at 0, 0. And we got our stuff. All right. Problems that you could look at for this stuff, it's page 373, 13 through 54, page 380, 15 through 55, page 390, 7 through 53. And just pick some of those, each little section, try to practice those. Canvas quiz will be up this week. You will have until test day to do your Canvas quiz. Still only 2 opportunities, but that gives you this week, and then you're on fall break next week, and then we come back on the 23rd, I think is correct, October 23rd for our Chapter 5 exam is the 23rd. Okay. If you weren't here and you missed getting your test back last week, they're laying right here. Come grab yours. The handwritten is your average up to that point. So